In this example, we are going to apply the Newton-Raphson method to determine the positive root of the quadratic equation. We have 5x squared plus 11x minus 17 is equal to 0. We are told to correct the three significant figures. Okay, then we need to also check our value by using the quadratic formula. So our function is here. We have 5x squared plus 11x minus 17. And we are saying, let us use the functional notation to get the first approximation of the root. So we have our function, which is f of x, and then we are going to substitute in x is equal to 0. We are starting from a point where x is equal to 0. So if we substitute in this one, use your calculator. So that will be where there is x, we put 0. So 5 times 0 squared plus 11 into 0, this gives you negative 17. That is 1. If we put x is equal to 1, okay, if we put x is equal to 1, here that means we have 1 squared times 5 plus 11 into 1 minus 17 is equal to negative 1. You can see how it is reducing. So what if we put in x is equal to 2? If we put in x is equal to 2, this will be 5 times 2 squared plus 11 into 2 minus 17. And we are getting 25. So you can see the value of the function has changed from negative to positive. So between that value, between the two values of x, from this x is equal to 1 up to x is equal to 2, there must be a value of x where the function is equal to 0, because you can see it is changing from negative to positive. Obviously, we know there must be a point where the function is 0. So that is the point that we need to look for. So that x value is the one that is going to give us the root of this function. Now, when we look closely at the two values, which of the two is close to 0? Because for the function to have this root, that root must make the function to be 0. So that means we need to look at the values of x. Which of the two gives a value of f of x that is close to 0? It is the one of x is equal to 1. So we are going to set the value of the first approximation. Our first approximation will be x is equal to 1. Now we already know the formula for Newton-Raphson. So that means our second approximation is equal to our first approximation of the root minus f of R1 divided by f prime of R1. But R1 is equal to 1. And we have to also look for the derivative, the first derivative of that function. So what is the first derivative of that function? Obviously, we are going to differentiate that. So we have 5x squared plus 11x minus 17. That is f of x. So what is f of x prime, or the first derivative? 2 times 5, isn't it?
Yeah.
Then x power 2 minus 1 plus 11 times x. This is 1 minus 1. Then obviously this, when differentiated, this is going to be 0. So this is going to be 10x plus 11, and that's all. So now we have to look for the value of f is equal to 1. I mean, of the value of f of 1. So by substituting in our value of 1, we already have that the function is equal to negative 1. Then we also know if we substitute 1, okay, into this function, the first derivative of x, then what is it going to be? It is going to be 10 times 1 plus 11, and this is going to give us 21. So if that is the case, so what are we going to do? We are saying our f of is equal to negative 1, f prime, or the first derivative of x at x is equal to 1 is 21. So what we do, we substitute in that formula. Therefore, our R2 will be R1, which is 1, minus FR1 is negative 1, divided by 21. So I get my value, negative 1 divided by 21. Divided by 21. Remember, this is R2 equal to 1 minus 0.0476. So this and that will cancel, and our R2 will be 1.0476. Now what is R3? So R3 will be R2 minus of R2 divided by F prime of R. That's what. So we need to look for F of R2. That means I'll get my 2. Okay, this is supposed to be 5. This will be 5 into 1.0476 squared plus 11 into 1.0476, then minus 17. So what will that be? I have 5 times 1.0476 squared plus 11 times 1.047 minus 17, and this is giving me 0.0010928. Make sure that you keep at least like 5 or 4 decimal places so that you maintain a good level of accuracy. Then we need to get f prime of R2. This is, we said it is 10, okay, 10x, so 10 into 1.0476 plus 11. So 1.0476 times 10 plus 11. And our answer is 21.476. So what is our R2? Our R2 is equal to, we already said, our R2, I mean R3, we said R3, so it's equal to R2, whereby R2 is 1.0476 minus, okay, FR2, which is 0.0109288, we divide it by 21.476. So if I get 0.0109288, I divide it by the value I had, 1 minus this answer. I'm getting a value which is 999 equal, but you redo with your calculator, you're going to find that this value is 1.47. So what you do, you repeat, okay? You repeat this. So when you repeat this, that means we are going the value of R4. So our O is therefore equal to R3 R3 divided by F prime R3. The R3 we have it. So what is F R3? This is the same as 1.04709 squared, obviously times 5, then plus we had 11 into 1 into x, so which is into 1.04709 minus 17. If I do that, 5 into 1.04709 squared plus 11 times 1.04709 minus 17, I'm getting a value FR3 giving negative 2.26, 2.6, let me say 6 times 10 to the power negative 3. Then I also need to get F prime of R3, which is the same as 11 into 1.04709 plus,
No, 10,
plus,
10, 10.
is it 10 or 11? 10, I think. Should be 10. So this is 10. So we get 10 times 1.04709 plus 11. So we are getting a value F prime R3, which is 21.4709. What we do, we put in this formula R4. So our R4 should equal to R3, R3 which is 1.04709 minus this negative 2.266 times 10 to the power negative 3. We divide it by 21.470. This one, this is telling us if we use our calculator, we have negative 2.266 exponent negative 3. We divide by that value, okay? Then we get 1.04709 minus this value. So what we get still keeps rotating around 1.047. That means the root of this function is going to be rotating around 1.047. Therefore, of the function fx equal to 5x squared plus 11x minus 17 is 1.05, and these are the three significant figures. When you use your formula of the quadratic equation, you should be able to get this value. Maybe I can try using the calculator, because the calculator uses that method to solve quadratic equations. The calculator uses the quadratic formula. So let me look for mode equation. I go to degree 2. The value of A is 5. The value of B, is 11. The value of C is negative 17. So when I calculate from the calculator, when I check from my calculator here, I see that the root is equal to 1.04709, and this is approximately 1.05 if we use 3 significant figures. So this is from the calculator, and this is from Newton. So you can see we are able to approximate the root of any function using Newton-Raphson method. What you have to keep in your mind is that you use the functional notation approach to estimate or to give a reasonable approximation of the first root. Then you use Newton-Raphson method using the first approximation to arrive at the final value. And how do you know that you have arrived at the final value? If you see there is no significant difference between, for example, the succeeding or the successive iterations. You can see the value of R3 and look at the value of R4. This R4 was giving me 1.0471. So when you look at the two, you see almost there is no significant difference. So you can stop at R4. Even if you do R5, you will be wasting time. It will remain around this value. So that's Newton-Raphson method for you. And I believe this is very simple. And if a question comes, you should be able